Hello and welcome to Chapter 3, Describing, Exploring, and Comparing Data. Because of the availability of powerful software and calculators, it is not necessary that we memorize formulas to calculate statistics or to manually calculate our statistics. So in this textbook, we will focus more on making practical sense of the result of our statistical analysis through critical thinking. Although we will learn the steps for important procedures, it will not always be necessary to master those steps. However, it will be helpful for you to better understand those procedures by performing a few manual calculations before using technology. In this section, we will develop the ability to measure the center of data by finding the mean, the median, the mode, and the mid-range. We will also determine whether an outlier has a substantial effect on the mean and the median. The focus of this section is to obtain a value that measures the center of a data set. In particular, we present measures of center including the mean and the median. Our objective here is not only to find the values of each measure of center, but also to interpret those values. A measure of center is a way to describe what's typical for a set of data. A measure of center doesn't tell you specifics about the individual pieces of the data set, but it does give you an overall picture of what's going on in the entire data set. We will review 4 measures of center, including the mean, the mode, the median, and the mid-range. The mean, or the arithmetic mean, of a data set is the measure of center found by adding all of the data values and then dividing by the total number of data values in the data set. For example, in this data set, we have data values of 2, 3, 5, 9, and 11. So the mean for this data set is the sum of those data values, 2 plus 3 plus 5 plus 9 plus 11, divided by the total number of data values in the data set. So we divide that sum by 5. That gives us 30 over 5, which equals to 6. So the mean for this data set is 6. Some important properties of the mean include: first, the sample means drawn from the same population tend to vary less than other measures of center. Second, the mean of a data set uses every data value in the data set. And third, a disadvantage of the mean is that just one extreme value or an outlier can change the value of the mean substantially. This is known as not being resistant. So we say that the mean is not resistant. A statistic is resistant if the presence of an extreme value or outlier does not cause it to change very much. Let's look at these 2 data sets. In the first data set, we have the values 2, 3, 5, 9, and 11. We've already calculated the mean for that data set to be 6. In the second data set, it looks very similar to the first, except we have 2, 3, 5, 9, and 51. When we calculate the mean for that data set, we get a mean of 14. So as you can see, that outlier of 51 did have an effect on the mean, and so that demonstrates that the mean is not resistant to extreme values. We can use notation to express the formula of the mean using the Greek letter uppercase sigma. Uppercase sigma indicates that the data values should be added together. Let's look at the notation we will use to express the mean. Uppercase sigma denotes the sum of the data values. Lowercase x is the variable used to represent the individual data values. N represents the number of data values in the sample, and uppercase N represents the number of data values in the population. Here we have 2 mean formulas. The first is x bar, and it is the mean of a sample data set. In statistics, we read this equation as the sample mean is equal to the sum of all observations in the sample divided by the sample size. Let's break this equation down into parts. X bar just stands for sample mean. The uppercase sigma is the notation for summation, which just means add everything up. In this chapter, the author uses X by itself to represent all of the X values. However, it's more common to use X with a small superscript I, an X with a small subscript I to represent all of the data values. And finally, in our equation, N is the number of items in the sample. So we have X bar, or sample mean, equals to the summation of all observations divided by the number of observations. The second formula is almost identical to the first, but this formula is for the population mean. The population mean is represented by the Greek letter mu. We read this formula as the population mean mu is equal to the sum of all observations in the population divided by the population size. Also notice that the population size is indicated by the uppercase N instead of the lowercase n. And you'll want to note that in sample statistics, we usually represent sample statistics by the English letters, and population parameters are usually represented by Greek letters. Let's consider this example. Dataset 32 of airport data speeds in Appendix B includes measures of data speeds from smartphones from 4 different carriers. If we find the mean of the first 5 data speeds for Verizon, we find 38.5 megabits per second, 55.6 megabits per second, 22.4 megabits per second, and 14.1 megabits per second, and finally 23.1 megabits per second. So now to calculate our sample mean, let's simply plug in to our equation. So we have X bar equals to the summation of all observations divided by the sample size. So we would have 38.5 plus 55.6 plus 22.4 plus 14.1 plus 23.1, all of that divided by 5. And so our mean for this sample is 30.74 megabits per second. So we would say that the sample mean of the first 5 Verizon data set, our data speeds, is 30.74 megabits per second. Although it is common for people to use the word average when referring to the mean, it is sometimes used for other measures of center. In general, the term average is not used by statisticians, and we should avoid using it for the remainder of this course when referring to any measure of center. If you were to review most professional journals, you would find that the authors rarely or ever use the term average. So make sure that you use the word mean when referring to the sample or population mean. The median of a data set is the measure of center that is in the middle of the data set when the original data values are arranged in order of increasing magnitude. So we have a data set here, and we've ordered them from smallest to largest value. So the median of this data set would be the value that would be right in the middle. In this case, since there is no value in between that middle between 28 and 29, we would simply take the mean of 28 and 29, and our median for this data set would be 28.5. Some important properties of the median include: first, the median does not change by large amounts when we include just a few extreme values. So we would say the median is a resistant measure of center. Second, the median does not directly use every data value. For example, if the largest value is changed to a much larger value, then the median would not change. Let's look at our data set before, and if we change the last data value from 34 to 74, you'll find that our median is still the same, 28.5. The median of a sample is sometimes denoted by x tilde, or with a capital M or MED. To find the median, the first thing we want to do is to sort the values in order, and then use the following two procedures. If the number of data values is odd, the median is the number located in the exact middle of the sorted data list. If the number of the data values is even, then the median is found by computing the mean of the two middle numbers in the sorted data list. Let's find the median of the first 5 data speeds for Verizon. Recall that our data set is 38.5, 55.6, 22.4, 14.1, and 23.1. To find the median of this data set, the first thing we want to do is to sort the data values by arranging them in ascending order as shown below. So we start with 14.1, and then 22.4, 23.1, 38.5, and finally 55.6. And because there are 5 data values, we have an odd number of data values in our data set. So the median is the number that is located in the exact middle of the sorted list. So that would be the third value in our sorted data list. So the median of this data set would be 23.1 megabytes per second. Let's repeat the previous example, but now we will add a 6th data speed of 24.5 megabits per second to our data set. Let's find the median of those data speeds. Again, our first step is to arrange the values into ascending order. So we go from 14.1 all the way up to 55.6. But now, because we have an even number of values in our data set, we will want to find the median by computing the mean of the two middle values. In this case, our two middle values are 23.1 and 24.5. So we simply calculate the mean of those two numbers. So we just add 23.1 plus 24.5 divided by 2, and our median is now 23.8 megabits per second. The mode of a data set is the value that occurs with the greatest frequency. For example, in this data set, we see that the number 21 appears 3 times, and so it's the most frequently appearing number in our data set. So for this data set, our measure of center known as the mode would be 21. The mode is not used very often with quantitative data, but it is the only measure of center that can be used with qualitative data. Two important properties of the mode include: first, the mode can be found with qualitative data, and second, the data set can have either no mode, or one mode, or multiple modes. A data set with one mode is called a unimodal data set. With two modes, it's a bimodal data set, and with more than two modes, it would be called a multimodal data set. When a data value occurs with the same greatest frequency in a data set, each one is a mode, and the data set is said to be bimodal. When more than two data values occur with the same greatest frequency, each is a mode, and the data set is said to be multimodal. When no data value is repeated, we say that there is no mode. Let's find the mode of these sprint data speed values. Our data set has a speed of 0.2, another 0.3, another 0.3, another 0.3, a 0.6, another 0.6, and finally a 1.2 megabits per second speed. As you can see, the value of 0.3 is the most frequently occurring value, so our mode of this data set would be 0.3 megabits per second. This first data set has two modes. We have 0.3 megabits per second, 0.3 megabits per second, 0.6 megabits per second, 4.0 megabits per second, and 4.0 megabits per second. So we would say that this data set has two modes, or bimodal. So one mode would be 0.3 megabits per second, and the second mode would be 4.0 megabits per second. This next data set has no most frequently occurring value, so we would say that this data set has no mode because no value is repeated. The mid-range of a data set is a measure of center that is the value midway between the maximum value and the minimum value in the original data set. It is found by adding the maximum value to the minimum value and then dividing by 2. Because the mid-range uses only the maximum and the minimum values, it is very sensitive to those extreme values. So we would say the mid-range is not resistant. Let's look at these two data sets of recorded daily temperatures. In example 1, we have a data set with a high value or a maximum value of 90 degrees and a low value or the minimum value of 55 degrees. So the mid-range of this data set is 90 plus 55 divided by 2 equals to 77 degrees. In our second example, we still have a high value of 90, and now our low value or our minimum value is 20. So this mid-range is 90 plus 20 divided by 2 equals to 55 degrees. So even though all of the other numbers are the same in the two data sets except for that first number, you can see how the extreme value of that first number in data set 2 drastically changed the mid-range value. So thus the mid-range is not resistant. Here are some important properties of the mid-range. In practice, the mid-range is very rarely used, but it has 3 redeeming features. The mid-range is very easy to compute. The mid-range helps to reinforce the very important point that there are several different ways to define the center of a data set. And the value of the mid-range is sometimes used incorrectly for the median. So confusion can be reduced by clearly defining the mid-range along with the median. Let's continue using our Verizon data set, and we'll find the mid-range for that Verizon data, the Verizon data speeds. We have, in that data set, we have a high value of 55.6 and a low value of 14.1. So our mid-range would be 55.6 plus 14.1 divided by 2 equals to 34.85 megabits per second. Let's review some rounding rules for measures of center. For the mean, median, and mid-range, carry one more decimal place than is present in the original set of data. For the mode, leave the value as is without rounding, because these values of the mode are the same as some of the original data values. So if we were to calculate the mean of this data set, we would get a value of 39.8333. So we would want to round that off to 39.8. For the median of this data set, we get a value of 32.5. So we'll leave it as one decimal place. And finally, for the mid-range, we would get a mid-range of 47. You could round that to 47.0, but it isn't necessary. And finally, our mode is 10, and so there's no reason to round that value because it represents some of the data in the original data set. We can always calculate measures of center from a sample of numbers, but we should always think about whether it makes sense to do this. Also, we should also consider about the sampling method that we are using to collect the data. Let's consider a couple of situations in which the mean and the median are not meaningful statistics. Let's consider zip codes. If we have the zip code of the Gateway Arch in St. Louis, the White House, the Air Force Division of the Pentagon, the Empire State Building, and the Statue of Liberty, and those zip codes are as follows: 63102, 2500, 2033, 2330, 10118, and finally 10004. Those zip codes don't measure or count anything. They're just labels for geographic locations, so you would never want to report an average zip code or a median zip code. It wouldn't make any sense. Let's also consider the ranks of selected national university, where Harvard is ranked 2nd, Yale is ranked 3rd, Duke is ranked 7th, Dartmouth is ranked 10th, and Brown is ranked 14th. Those ranks, 2nd, 3rd, 7th, 10th, and 14th, are just in order and don't have any measurement or count. So we wouldn't want to calculate the mean or the median for this data set either. When working with data summarized in a frequency distribution, we will make the calculations possible by pretending that the sample values in each class are equal to the class midpoint. So the sample mean for our new formula is x bar equals to the summation of the product of the frequency times the midpoint over the summation of all the frequencies. So in this formula, our f is the frequency of the class, x is the midpoint of the class, and also in this formula, we will calculate our numerator first by multiplying each frequency with the class midpoint, and then summing those products. For the denominator, we just get the sum of all of the frequencies. Let's go back to our example from Chapter 2, the McDonald's lunch service times. Recall that we found the midpoint for each class in that distribution. So we can use this information to find an approximation of the mean service time. In this table, we have the information we need to calculate our approximate mean. We start by multiplying the frequency of our first class with the midpoint of our first class. That is 11 times 99.5 equals to 1094.5. We do this for each class, and and then we sum all of those products. At the bottom of the last column on the right, we have the value for our numerator, 8,025. And then to finish off our equation, we just sum all of the frequencies in our second column to get our denominator. In this example, it is 50. Now let's look at the formula for the mean of a frequency distribution. We have x bar equals to 8,025 divided by 50. That equals to 160.5 seconds. So we would say that the mean service time is approximately 160.5 seconds. The weighted mean is a kind of a mean, but instead of each data point contributing equally to the final mean, some of the data points contribute more weight than others. And we can compute the weighted mean with this formula where the mean equals to the summation of the product of W times X over the summation of W. In this formula, W is equal to the weight and X is the corresponding value. Let's consider this example. In her first semester of college, a student took 5 classes. Her final grades, along with the number of credits for each course, were as follows. For her first class, she got an A, and it was a 3-credit course. Her second class, she got an A, and it was a 4-credit course. Her third class, she received a B, and it's a 3-credit course. Her fourth class is a C, and it is also a 3-credit course. And finally, her fifth class was an F, and it was a 1-credit course. The grading system assigns quality points to each letter grade as follows. An A equals to 4, a B equals to 3, C equals to 2, and D equals to 1, and finally F equals to 0. So let's compute her grade point average. In this example, we will use credits for each class as the weights and the numeric equivalents of the grade as the X values. To calculate the weighted mean, we will take each grade equivalent and multiply it by the credit. So in the column all the way to the right, we have the product of the weight times the observation. So for class 1, she had 3 credits and her grade was an A, so it's 3 times 4. For class 2, it was a 4-credit class and she got it an A, so it's 4 times 4. We do that for all 5 classes, and then we sum up the total of the last column on the right. We also need the summation of the total of the weights. So we sum up that second column, that third column where credit is considered weight. So in the end, our sample mean is 43 divided by 14 equals to 3.07. So her GPA for that semester was 3.07. Although we would normally round this value to 3.1, typically it's common to have the GPA represented by 2 or 3 decimal places. So in this example, we'll leave her GPA as 3.07. This is the end of Chapter 3, Section 1. Please proceed to Chapter 3, Section 2.